Hello everyone, I am Dr. Krishna Sarker. Here in this session, I'll be going to discuss about transfer function calculation from electrical RLC networks with poles and zeros models. This is linear control systems, problem number 4. Lecture series on linear control systems and lecture number 16. So our topics: transfer function calculation from electrical RLC networks with poles and zeros models. Transfer function calculations. This is example 4. Find the transfer function of the given electrical networks. This is the given electrical networks: VIT, input voltage, R resistance, L inductance, C capacitance, and V0T output voltage. This is also phase lag networks. VIT equals to input voltage and V0T equals to output voltage. So our target transfer function calculation, that means V0T divided by VIT. Laplace transformation of V0T. Laplace transformation of V0T divided by Laplace transformation of VIT. Output voltage divided by input voltage, and all initial conditions are zeros. So, solution. Procedure for finding transfer function of electrical networks. Solution. Step 1, this is step 1, and point 1, the given electrical network as shown in figure A, and determine the transfer function. So this is the figure A, determine the transfer function. This is given electrical networks, and the first network's time domain and second network frequency domain or S domain. Then draw the given networks figure B in the S domain with each inductance by SL and each capacitance by 1 by SC. So this is the frequency domain electrical circuit. L, each inductance by S of L. So this is the S of L, and each capacitance by 1 by SC. This is the frequency domain configuration. Then use KCL, KVL, mesh analysis, nodal analysis to write network equation. By using KCL, KVL, mesh analysis or node analysis, write the network equations. Solve the simultaneous equation to the transfer function. Then solve simultaneous equation and determine the transfer function of these systems. So step 2, apply KVL in mesh 1 of the given networks. Apply KVL in mesh 1. This is the loop current I of t, and this is mesh 1. So apply KVL in mesh 1 and we get V0T. This is the V0T. V0T equivalent to what? V0T equivalent to R into IT plus resistance, corresponding resistance drop, and L into dit dt plus 1 by C into IT dt. This is for capacitance. So for inductance, this part for inductance, and for capacitance, This is for capacitance part. 1 by C into IT into dt. So VIT, input voltage, equals to R into IT plus L into di dt plus 1 by C into IT dt. Then what is the output voltage? Apply KVL in mesh 2. Apply KVL in mesh 2. This is the mesh 2. And this is the mesh 1. Apply KVL in mesh 2. And we get in mesh 2 1 by C into IT dt. This is the equation number 2. So output voltage V0t equals to 1 by C integration IT dt. Transfer function calculation. Then taking step number 3, taking Laplace transform of equation 1 and 2 with assumption that all the initial conditions are zeros. So taking Laplace transform, this is the equation number 1 already discussed, and this is the equation number 2. So equation 1, taking Laplace transform both sides, and we get Vi of s, Vi of t corresponding Vi of s, and Rit equivalent to Ris and I of s plus L into ddt equivalent to s, and Laplace transform of it equivalent to I of s, and then plus 1 by c it dt integration is by s. So this is the equation number 3, and Laplace transform corresponding equation 1. Then output equation V0t and the Laplace transform V0s equals to 1 by C into it dt. It dt equals to equivalent to Is by S. So this is the equation number 4. This is the equation number 4. V0t, Laplace transform of V0t equivalent to V0s, and Laplace transform of it dt, integration it dt equals to Is by S, and constant value 1 by C, and constant value 1 by C. This is the equation number 4. So what is the transfer function? Definition of transfer function: Laplace transform of output. Here in this case, this is the Laplace transform of output V0s, and Laplace transform of input Vi of. So V0s by Vis. What is the value? What is the transfer function? Definition of transfer function: transfer function equals to Laplace transform of output divided by Laplace transform of input, and all initial conditions are zeros. And another definition: Laplace transform of output response or effect divided by, this is also called excitation, Laplace transform of input variable of, or this is the cause. Laplace transform of input means cause and output means effects, and input means excitation. This is the excitation part, and all initial conditions 0. So by definition, we can easily write output by input voltage V0t, V0s divided by Vis. So output voltage V0s divided by Vis equivalent to what? 1 by SC, 1 by SC into Is plus R into Is plus S into L into I of S plus 1 by SC into I of S. So this is the output by input voltage. This portion Vis, this is denominator part, and this is the numerator part, output voltage. Then common I of S, we get cancel Is, and we get 1 by SC, R plus LC plus 1 by SC. Finally, 1 by RC into S plus LC into S square plus 1. This is the second order characteristics equation. And therefore, the transfer function of the RLC network is given by V0s by Vis equals to 1 by LC into S square plus RC into S plus 1 equivalent to G of S, equals to G of S. This is the transfer function for RLC given network. Transfer function calculated by the block diagram representation is shown in figure. This is the VI of input voltage, or this is also called cause, or this is also called excitation, and the block 1 by S square plus Bs plus C, and the V0 is equals to output voltage. In control system language, this is R of S, input voltage R of S, and this is the C of S, control output voltage C of S. Then transfer function of the network is given by V0S by VIS equals to 1 by S square plus Bs plus 1, where A equals to L into C plus B equals to R into C, where S is equal to, this is the second order systems, that's why 2 poles, and S, or this is also S1, S2, 2 values, S1 comma S2, suppose equivalent to minus B plus minus root over B square minus 4A by 2 into A, minus B, this is the minus B plus minus root over B square, this is also B square, minus 4AC, 4A C, C equals to 1 by 2 into A. So S is equal to minus B plus minus root over B square minus 4A by 2 into A. Then from the transfer function 1 by S square plus Bs plus C, and S is equal to this, here number of zeros equals to 0. That means numerator power S to the power 0, S to the power 0, and this is equivalent to M, and denominator power AS square, and this is equivalent to N. So N equals to 2 and M equals to 0. So N greater than M, N greater than M. Numerator power greater than denominator power. Denominator power, sorry, in this case, denominator power N greater than numerator power. So if the order of the numerator polynomial is less than the order of the denominator polynomial, the transfer function is called strictly proper transfer function. Strictly proper transfer function, this is called. And the transfer function, pole 0 location, this is the real axis and this is the imaginary axis. What is the position of poles? Here, number of zeros less than number of poles, that means P greater than zeros. The above transfer function having the simple poles are at, what is the position of poles? What is the position of poles? In this case, first case, S1 and S2 are complex conjugate having negative real part. And second condition, S1 and S2 are complex conjugate having positive real parts. Third point, S1 and S2 are real and lie in the left hand side of the S plane. S1 and S2 are real and lie in the right half of S plane. S1 and S2 are roots become repeated either positive side or negative side or imaginary axis. S1 and S2 are complex conjugate roots and on the j omega axis. And S1 lie in the right half and S2 lie in the left half or left hand side. So from the transfer function, V0S by VIS equals to 1 by S square plus Bs plus 1, and S is equal to, first case, S1 and S2 are complex conjugate having the negative real part, and the pole 0 location, this is the real part, this is the imaginary part, this is the pole 0 location S1 and S2, because S1 S2 complex conjugate having negative real part. Suppose this is equals to minus A plus Bj, and this is equivalent to minus A minus B of J. So this is the pole 0 location. And another second case, S1, S2 are complex conjugate having positive real parts. So this is the real axis, this is the imaginary axis, and this portion actually complex conjugate having positive real parts. So this is the S1, S2 complex conjugate and right hand side of the S-plane. So first case, this is the stable system because all the poles left hand side of the S-plane. So this is stable. But in this case, all the poles right hand side of the S-plane. That's why this system, in this case, this is the unstable. Next, case number 3. S1 and S2 are real and lie in the left half of S-plane. So this is the real axis, this is the imaginary axis, and S1, S2 are real. This is the real axis, lie in the left half. This is the left half or left hand side of the S-plane. So S1 equals to this and S2 equals to this. Similarly, S1, S2. Similarly, for 4, S1 and S2 are real and lie in the right half of the S-plane. Real axis, this is the imaginary axis, and this is the right hand side of the S-plane. And again, this system stable, all the poles left hand side of the S-plane, and in this case, all the poles and zeros right hand side of the S-plane. So this is the unstable case. And case number 5, when S1 and S2 becomes repeated roots, that means this types S plus A whole square. That means S is equal to minus A or minus A. For real, if imaginary, then this is the real axis, this is the imaginary axis. So repeated roots at same position, S1 equals to S2. Similarly, right hand side, for right hand side condition, this is also repeated roots, S1 and S2 equal distance. Then case number, S1 and S2 are complex conjugate roots and on the j omega axis. This is also very important because two roots on the j omega axis, this is S1 and this is the S2 position, and j omega axis. This is also called j omega imaginary or j omega axis. And another case, real and imaginary, S1 lie in the left half of the S-plane, and S2, this is the S1 left hand side, and right, this is the S2 right hand side. For in this case, this is the sustained oscillation. Yes. So pole and zeros of a transfer function. The transfer function of a control system is defined as the ratio of Laplace transform of output variable response or effect to the Laplace transform of input variable, that is excitation, assuming that all the initial conditions to be 0. A 0 is indicated by a small circle, and the point at which the denominator polynomial P of S equals to 0 are called the poles of the systems. The poles are indicated by the small cross. So at 0, the transfer function becomes 0, and at poles, it becomes infinity. The denominator polynomial of the transfer function is called the characteristics polynomial. So this is the pole 0 of the transfer function. Thank you.